In this final segment, we'll go beyond the 7% covered by local superclusters and examine the universe as a whole. At the end, we'll quickly review all the territory we've covered since we began our journey exploring the dimensions of the Earth. So let's start with a look at some of the objects photographed by Hubble that lay beyond our local superclusters. This optical image shows the massive galaxy cluster Abell 2029. This galaxy cluster has a redshift that indicates that it is 1 billion light-years away. The large elliptical galaxy visible in the center of the image is IC 1101. It is the largest galaxy ever seen. It is 6 million light-years across, 60 times larger than our Milky Way, and it contains around 100 trillion stars. You might recognize NGC 4319. It is a galaxy in the Virgo supercluster. Of interest now is the small light at the upper right. It's the quasar called Markarian 205. It's 1.1 billion light-years away. Markarian is a relatively nearby quasar. Many quasars reside much further away. Quasars are the intensely powerful centers of distant active galaxies, powered by a huge disk of particles surrounding a supermassive black hole. As matter from the disk falls inward, some quasars, including this one, have been observed to fire off superfast jets into the surrounding space. In this picture, one of these jets appears as a dusty streak measuring some 200,000 light-years in length. Despite its great distance, 3C273 is still one of the closest quasars to our home. It was the first quasar ever to be identified and was discovered in the early 1960s. Quasars are capable of emitting hundreds or even thousands of times the entire energy output of our galaxy, making them some of the most luminous and energetic objects in the entire universe. Of these very bright objects, 3C273 is the brightest in our skies. This is a combined ESO Very Large Telescope and Chandra image of the newly discovered galaxy cluster called El Gordo. It consists of two separate galaxy subclusters colliding. We are seeing what this cluster looked like when the universe was only half its current age. Hubble is a supernova machine for probing the early universe. Here's a Type 1a it found that's approximately 8 billion light-years from Earth. If you recall, Type 1a supernova represent one of our most important standard candles because they are so bright we can see them from very far away. In 2013, Hubble broke the record in the quest to find the furthest Type 1a with the discovery of SN UDS 10WIL, a supernova that exploded more than 10 billion years ago, at a time when the universe was in its early formative years and stars were being born at a rapid rate. The image at the far left shows the host galaxy without the supernova. The middle image, taken a year later, reveals the galaxy with the supernova. The supernova cannot be seen because it is too close to the center of the host galaxy. To detect the supernova, astronomers subtract the first image from the middle image to see the light from the supernova alone, shown in the image at the far right. You'll remember the Einstein ring we saw around ESO 325-G004 in our segment on local superclusters. The ring was the image of a more distant galaxy. The arc shape was created by the bending of the background galaxy's light by the gravity of the massive foreground galaxy. The process is called gravitational lensing because the mass between us and the background galaxy behaves just like an optical lens. This same light bending leads to the warping of light from distant galaxies, as the light encounters supermassive galaxies on their path to us. Here's a clip that shows how this lensing works on a grand scale. A distant galaxy would be seen here on Earth directly if there were no intervening massive cluster to bend the light. But with such a cluster, the light from the distant galaxy gets bent into rings and arcs that continue on to the Earth. This is Abell 1689, 2.2 billion light-years away. It's one of the most massive galaxy clusters known. Its gravity acts like a 2 million light-year wide lens in space. Here again we see how the gravitational field surrounding this massive cluster of galaxies acts as a natural lens in space to brighten and magnify the light coming from very distant background galaxies. In this photo, the galaxy is visible twice because its light followed two separate paths around Abell 68 before reaching us. This is a close-up look at the brightest, distant, magnified galaxy in the universe known to date. It is one of the most striking examples of gravitational lensing. In this image, the light from a distant galaxy, nearly 10 billion light-years away, has been warped into a nearly 90-degree arc of light in the galaxy cluster. The galaxy cluster that is bending the light lies 5 billion light-years away. And here's another cluster, 5.7 billion light-years away. These foreground galaxy clusters are magnifying the light from the faint galaxies that lie far behind the clusters themselves. These faint lensed galaxies are around 12 billion light-years away. It's the gravitational lensing that allows us to see that far back in time. Without the magnification, these galaxies would be invisible for us. This Hubble image shows a massive galaxy cluster about 4.6 billion light-years away. Along its border, 4 bright arcs are visible. These are copies of the same distant galaxy, nicknamed the Sunburst Arc. It's almost 11 billion light-years away. Its light is being lensed into multiple images by strong gravitational lensing. The Sunburst Arc is among the brightest lensed galaxies known, and its image is visible at least 12 times within the 4 arcs. Here's a closer look at 3 of them. The lens makes various images from 10 to 30 times brighter. This allows Hubble to view structures as small as 520 light-years across, a rare detailed observation for an object that far away. Until the early part of the 20th century, it went without saying that the matter we see is most of the matter there is. That would be protons and neutrons, with accelerating electrons creating the light we see. But that came into question in the early 1930s, when Fritz Zwicky, a Swiss astronomer out of Caltech, studied the Coma cluster, 321 million light-years away, with 1,000 galaxies spanning 25 million light-years in diameter. He looked at it in a number of ways, 2 of which are very revealing. In one, he used galaxy motion to calculate mass, and in the other, he used galaxy luminosity to calculate mass. His processes are not precise, but they do provide ballpark figures for the mass of the cluster. For motion, he had the cluster galaxies' radial velocities from the Doppler shift in the light we see. He then generalized them into their 3-dimensional velocity dispersion statistical equivalent. This galaxy motion gives us the kinetic energy for the cluster. Zwicky used the well-understood virial theorem that has the kinetic energy of a system equal to 1/2 its gravitational potential energy. This allows us to solve for the mass of the cluster. This is the mass as measured by its gravitational effects. The second way he calculated the cluster's mass was to use the cluster's luminosity. You may recall from our discussion on the Hertzsprung-Russell diagram in our How Far Away Is It segment on distant stars that there is a relationship between a star's mass and its luminosity. We can use that relationship to estimate the mass of groups of stars by measuring their luminosity. We use the mass-to-light ratio of the Sun as the base for comparisons. Zwicky measured the luminosity of the average galaxy in the Coma cluster. Using a mass-to-light ratio of 3, he calculated its mass. When he multiplied the average times 1,000 galaxies in the cluster, he came out with a number that was over 100 times less than the mass calculated via the virial theorem based on gravity. In other words, the motion of the galaxies in the cluster indicated a mass that was over 100 times the mass from luminous matter. Zwicky concluded that either the laws of gravity as we know them, Newton's and Einstein's, did not work for volumes as large as the Coma cluster, or the luminous matter is only a very small part of the total matter of the cluster. He called the rest of the matter dark matter, and suggested that gravitational lensing could help quantify this dark matter. But back in the 1930s, nobody believed him. With this new understanding about the possibility and impact of dark matter, astronomers turned their attention to galaxy clusters like the one studied by Zwicky in 1936. Our case-in-point galaxy is known as the Bullet cluster. The virial motion of its galaxies indicates that a collision has occurred. Two massive clusters have passed through each other millions of years ago, and member galaxies are now flying apart. If we zoom in a bit closer, we can see the telltale arcs of more distant galaxies lensed by the gravity of the Bullet cluster. Counting the lensed objects and the estimated amount of light bending involved for each one, a map of the area containing most of the mass of the cluster can be superimposed. We have used blue to indicate the locations where the vast majority of the matter must be located in order to get the observed lensing. Here we have the cluster's hot X-ray emitting gas detected by the Chandra X-ray Observatory. The two pink clumps contain most of the normal matter, sometimes referred to as baryonic matter, or matter made up of protons and neutrons. The bullet-shaped clump on the right is the hot gas from one cluster, which passed through the hot gas from the other cluster during the collision. When we superimpose the dark, baryonic, and visible components of the cluster's mass, we get the full picture. The galaxies and the dark matter have traveled a great deal further than the gas. This indicates that the galaxies and dark matter in the two colliding clusters did not interfere with each other. In other words, they passed through each other without slowing down. On the other hand, during the collision, the gas clouds were slowed by a drag force, similar to air resistance. This combination had the effect of separating the gas from the dark matter. This separation is considered to be direct evidence that dark matter exists. Measurements indicate that the galaxy clusters on average have 85% dark matter, 14% intergalactic gas, and only 1% stars. In 2014, a team of astronomers found a supernova in this galaxy cluster, over 5 billion light-years away. The supernova actually happened in a galaxy 4 billion light-years beyond that, making it 9 billion light-years away. The huge mass of the foreground galaxy and galaxy cluster bent the light from the distant supernova, creating 4 separate images of the same explosion. The images are arranged around an elliptical galaxy in a formation known as an Einstein cross. Following this discovery, astronomers modeled several possible gas and dark matter distributions in the galaxy cluster. Each model predicted that another image of this supernova will appear in the cluster, but they had different time estimates ranging from 2015 through 2025. In December 2015, it appeared. For the first time in history, the time and location of a supernova was accurately predicted. We actually saw the supernova happen. Instead of detecting a flash in the sky and turning telescopes to its location, we had the telescopes already focused on the correct area and recorded the event from beginning to end. This was powerful evidence for dark matter. In the late 1920s, Edwin Hubble discovered that except for a few nearby galaxies, all galaxies were moving away from us, and the further away they are, the faster they are moving, along with the assumptions that there are no preferred places and no preferred directions in space. This means that all galaxies, not bound together by gravity, are moving away from each other. The flow of all galaxies away from each other, with faster velocities the further away from each other they are, cannot happen in a fixed volume, because in a fixed volume, some reference frames would have to have distant objects heading towards them for others to have them moving away. It can only be explained if the space that these galaxies exist in is itself expanding. Here's a one-dimensional example to illustrate why this is the case. Consider an 8-meter circle with marks 1 meter apart. If we are at the top mark and all the other marks are moving away from us, then, from other points of view, marks are getting closer. The system is not homogeneous. But if the apparent motion is due to the amount of space expanding, we get a different picture. Here, the marks hold their position on the line, but the line grows. Let's say each meter on the line expands to 2 meters over the course of a minute. We see that the distance between adjacent marks goes up 1 meter, and their apparent velocity, as seen by each other, is 1 meter per minute. But more distant marks have increased their distance and velocity by more than that. And the further away any 2 marks are, the more their distance and velocity have increased. And most importantly, this will be the same no matter which mark is used for the reference frame. In order to illustrate the point, this example uses an expansion rate that is 74,000 trillion times greater than the actual expansion rate as determined by the Hubble constant. The real expansion is very slow. If we take a look at what the expansion does to 1 meter, we see that it would take 1,000,000 years to expand by just 7/millionths of a meter. That's way too slow to ever notice or even measure in a lab in a lifetime. And it is why it's so easy to overcome it with local gravity out to the Andromeda galaxy. It should be noted that this expansion of space itself does not pull apart objects that exist in that space. A meter stick does not expand. That's because the size of the meter stick is determined by the forces that hold it together, and these forces are not changing. Expanding space has significant implications for measuring distance. Here we are zooming into GNZ11, the most distant object ever found. The galaxy's redshift combined with Hubble's law, gives us the distance the light traveled, 13.4 billion light-years. And we know the speed of light, so the time traveled was 13.4 billion years. We normally say that the galaxy is therefore 13.4 billion light-years away. But during its long travel time, space expanded considerably. In fact, GN-Z11 was less than 2.7 billion light-years away from us when the light started its journey, and the galaxy is now over 30 billion light-years away. In order to calculate these distances, we need to know how the universe expanded during the light's journey. Note that if a galaxy is far enough away, its apparent velocity will be faster than the speed of light, and its light would never reach us. It would be beyond the physical visible horizon for the universe. It's not that it is moving through space that fast, it's just that more space is being created per second between us and them than light can traverse in 1 second. Plugging in the numbers, we find that all galaxies beyond 14 billion light-years could never be seen here. GN-Z11 is now 32 billion light-years away, so the light that is leaving GN-Z11 now will never reach us. After Hubble discovered the universe was expanding, it was assumed that it started off with a tremendous expansion rate, and because of the gravitational attraction of all the matter in the universe, the expansion would be slowing down. Two major efforts were started in the late 1990s to prove that the universe's expansion was decelerating. Both groups used distant Type 1a supernova as their standard candles. Supernovae provide a luminosity reading that enables us to determine their distance via the inverse square law. This distance is called the luminosity distance. Type 1a supernova also provide a redshift reading that gives us the distance via Hubble's law. Luminosity and redshift combined can tell us if the universe's expansion rate is constant, decelerating, or accelerating. Here's how it works. First, we measure the luminosity of a distant Type 1a supernova like SN 1994d and measure its redshift. Then we map the distance between us and the supernova over time. If the expansion rate is constant, the luminosity distance and the redshift distance will be the same. But if the expansion is slowing down, the expansion rate in the past would have been greater than what we see now, which means it would have taken a shorter time to expand from its size at light emission time to its present distance compared to a non-accelerating universe. This would result in a shorter light traveled time, shorter distance traveled, and a brighter observed supernova compared to a non-accelerating universe. By the same token, if the expansion is speeding up, the expansion rate in the past would have been smaller than what we see now, which means it would have taken a longer time to expand from its size at light emission time to its present distance compared to a non-accelerating universe. This would result in a longer light travel time, larger distance traveled, and a dimmer observed supernova compared to a non-accelerating universe. This is what both studies found. The universe is expanding, and the expansion is accelerating. In order to more precisely analyze our expanding universe, modern cosmologists place a grid over three-dimensional space. We treat the distance between two galaxies, r, as a constant. Then, we set the grid's scale factor, a, equal to 1 at the present time, and vary it to account for changes in distance over time instead of changing r. Now consider a cube enclosing a volume of space containing some number of galaxies. With our scale factor approach, the amount of matter inside the volume remains the same as the volume increases or decreases. But the matter density goes down when the scale factor increases, and it goes up when the scale factor decreases. We see that the matter density depends on the scale factor. Unlike matter that moves through space, photons are attached to the space they propagate through. So an expanding space will impact photons in a way that does not affect matter. Here's a cubic volume of space with a photon inside. The photon's wavelength, lambda, is equal to the length of the cube, a. Its energy is equal to Planck's constant times the speed of light divided by the wavelength. As the wavelength increases with an increase in the scale factor, the energy decreases, unlike matter where it remained constant. We see that the energy density also depends on the scale factor. In fact, we see that the scale factor, A, is the only variable. In other words, the history of the universe comes down to the history of the scale factor. And the history of the scale factor depends completely on the contents of the universe and how that content affects the space it exists in. When we observe light from distant galaxies, we are seeing the light from the stars in those galaxies, and that light has absorption lines. The same lines measured in a lab give us the wavelength of the light at the time it was emitted. A stretching of the wavelength creates a shift in the spectral lines to the red. For our nearby galaxies, light travels for a relatively short period of time, so the stretching due to space expansion is small. Our use of the Doppler effect that shifts spectral lines as the basis for determining radial velocities provides excellent measurements. But as the distance increases to hundreds of millions and billions of light years, space expansion becomes the dominant factor. In either case, we continue to measure redshift, z, as the difference between the wavelength emitted and the wavelength observed, divided by the wavelength emitted. In this hypothetical example, we have an object with a redshift equal to 6. Once a model for the change in the cosmic scale factor over time is specified, redshift gives us a great deal of information. For now, we'll assume a flat, matter-dominated universe. First, redshift gives us an object's receding velocity. With our model, we have the object moving away at 6 times the speed of light. Redshift also gives us the actual cosmic scale factor at the time the light was emitted. It gives us the age of the universe at the time the light was emitted. And it gives us the amount of time the light was traveling. Redshift gives us the distance to the object at the current time, and it gives us the distance to the object at the time the light was emitted. You can see why astronomers rely so heavily on redshift measurements. We now ask, what could be accelerating the expansion of the universe? In the How Small Is It video book chapter on the Higgs boson, we covered how so-called empty space is actually filled with matter and energy fields. We model the waves in these fields as quantum harmonic oscillators. And, given the Heisenberg uncertainty principle, the zero-point energy for any wave in the field must be greater than 0. We have seen that radiation and matter in the universe are diluted as space expands. But zero-point vacuum energy does not dilute. In fact, the total amount of vacuum energy increases as the volume of the universe increases. In a small universe, it would have little impact. But today, it is estimated to be around 70% of the energy density of the entire universe. This zero-point quantum vacuum energy is called dark energy, and it is enough to force the cosmos into its accelerating expansion. As we observe the space around us, we see our solar system, our galaxy, and our local group of galaxies first. We then see significant numbers of large, well-formed galaxies in our local supercluster. The further out we see, the further back in time we go. And the further back in time we go, the more we notice a reduction in the size and structure of the galaxies. Eventually, we reach as far as the first galaxies to ever form from the first stars that started to shine. Before that was just hydrogen and dark matter. No light was being created for us to see. As we look back in time, we are also looking back at an ever-shrinking volume because the universe was getting smaller, and its temperature was getting hotter. Eventually, it reached 3,000 degrees. At that point, hydrogen atoms began to dissociate into protons and electrons, and space became opaque. Coming back the other way, the surface where the transition from opaque to transparent occurred is called the surface of last scattering. At that time, all the photons in the universe were released. These photons are still with us today. We see them all across the sky in tremendous numbers. They are the cosmic microwave background photons, CMB, and they tell us a great deal about the past, present, and future of the universe. Here's a projection of the celestial dome, as seen by the Wilkinson Microwave Anisotropy Probe, factoring out all local and local group motion. The mapping preserves the relative sizes of the surface objects. The key observation is that the light fits the blackbody radiation curve perfectly. This gives us the temperature of the radiation today. It is 2.725 degrees. We know that at decoupling it was 3,000 degrees. So the temperature has been reduced by a factor of 1,100. So the universe has expanded by a factor of 1,100 times since decoupling. The blackbody radiation formula also gives us the number density of CMB photons. There are over 400 million of them in every cubic meter of space throughout the cosmos. This is 1,000 times more than all the photons from all the starlight ever created by all the stars and all the galaxies for all the billions of years that stars have been shining. The CMB redshift tells us that the light we see now was only 42 million light years away from our location when it was emitted. It traveled for just under 13.8 billion years to reach us, and its starting location is now 46.5 billion light years away, making the diameter of the visible universe 93 billion light years. The Planck satellite measurements detected small amounts of temperature deviation. The image uses color to show variations from the average, with blue for minus 200 millionths of a degree through green and yellow to red, which represents plus 200 millionths of a degree. That temperature deviation comes to 1 part in 100,000. These temperature deviations come from equally small mass density deviations in the plasma at the time of decoupling. We see large structures, small, even tiny structures, and giant structures. We even see structures within structures at every scale. In other words, they're quite fractal. These differences in the CMB are what led to the large-scale structures such as galaxy clusters, filaments, and voids that we see today. For example, a very tiny spot of red on the surface of last scattering, representing a small decrease in mass density in that region, will have expanded 1,100 times to the size of the Coma cluster today. Just how the universe evolved from small-scale matter deviations at the time of decoupling to filaments of superclusters and vast voids can be explained by a physical process called caustics. Originally developed to explain light behavior, it works just as well for protons and dark matter. I see this phenomena in my own backyard. The lines at the bottom of a swimming pool are examples of caustics caused by small waves on the surface of the water. And when we extend this to 3 dimensions, we get curved surfaces with increased density that intersect along lines that intersect at points. This is the web-like pattern we see in the large-scale universe. By collecting distances to thousands of galaxies in a narrow strip of the sky, it is possible to produce a slice of the universe, like this one from the 2DF Galaxy Redshift Survey. In 2003, this survey looked out into the universe to 3.5 billion light-years. Between 2000 and 2008, the Sloan Digital Sky Survey conducted one of the most ambitious and influential surveys in the history of cosmology. Over 8 years of operations, it obtained deep, multicolor images covering more than a quarter of the sky and created a 3-dimensional map containing more than 1 million galaxies. These are the color-enhanced slices through the survey's 3-dimensional map of the distribution of galaxies. Earth is at the center, and each point represents a galaxy. Galaxies are colored according to the age of their stars, with the redder, more strongly clustered points showing galaxies that are made of older stars. The outer circle is at a distance of 2 billion light-years. The region between the wedges was not mapped by the survey because dust in our own galaxy obscures the view of the distant universe in these directions. Working with the Virgo consortium of scientists from the Max Planck Institute in Germany, the survey put every data point into a supercomputer and produced the largest 3D image ever created. Here we are zooming into and panning across that image. Here you cannot see individual galaxies or even galaxy clusters. What we see are superclusters linked together in filaments or walls in a gigantic cosmic web. In this view of the cosmos, the Great Virgo supercluster is just a dot. There are more stars in the universe than there are grains of sand on all the beaches of Earth. This is the big picture of our universe as we understand it today. We've come a long way from our start triangulating and directly measuring sizes in my backyard in our segment on the Earth. In this segment, we split redshift, our final rung of the cosmic distance ladder, into 2 parts. The original was based on the Doppler effect. The second is cosmological redshift based on the expansion of the universe. It is important to remember that this kind of redshift can only provide distance information if we have a cosmological model for the expansion. And we do. It's called the Lambda Cold Dark Matter Benchmark Model. It is covered in depth in the How Old Is It video book. All this reminds me of Edwin Hubble's own words in 1936. They are still appropriate today. Thus, the explorations of space end on a note of uncertainty, and necessarily so. We are, by definition, in the very center of the observable region. We know our immediate neighborhood rather intimately. With increasing distance, our knowledge fades, and fades rapidly. Eventually, we reach the dim boundary, the utmost limits of our telescopes. There, we measure shadows, and we search among ghostly errors of measurement for landmarks that are scarcely more substantial. The search will continue. Not until the empirical resources are exhausted need we pass on to the dreamy realms of speculation.